Okay, so this question is asking a few things. The first one is to recognize that bromine, Br2, with light are the conditions that are typically used to do a radical bromination. And really, that's the only type of bromination we can do when we have an alkane. So an alkane is not very reactive towards bromine unless you split that Br2 molecule up into its radical components. So these two components will come together to make bromine radicals. And they're going to do, you're going to go through a radical chain process and you're going to get bromination of the alkane. Okay, now the next thing is, well, for this question, we're probably, in most exam situations, you'd be asked, what is the product of this reaction? You might be asked the mechanism as well. But even if you're just asked for the product, you might need to draw out the mechanism to work out what the likely product is. So I've done the first step. I've split the Br2 up into two bromine radicals. And then we want to look at this alkane and look at what CH bonds are available for reaction with those Br radicals, those bromine radicals. So if I redraw this alkane down here with all of the hydrogens in. So I've got one hydrogen there, and then I've got CH3 groups in all the other positions. Okay, now it's really important you draw out those hydrogens or recognize they're there, because this immediately tells you there's only two types of hydrogen in this molecule. Okay, there are methyl hydrogens and then there's one hydrogen here that is at a tertiary center. So that is attached to a tertiary carbon on there. So we wouldn't really say tertiary hydrogen, that doesn't really make sense, but the hydrogen is attached to a tertiary carbon, and that makes that CH bond weak. And talking about it from the stability point of view, if we make a radical at that center, we know that tertiary radicals are more stable than secondary and more stable than primary and methyl. So methyl radicals are extremely unstable and tertiary are quite stable. So we're going to prefer making radicals at that position there. So if we wanted to draw out a mechanism for this, we could. So let me just redraw that again, use a different color. And I won't draw in those methyl hydrogens now. I'm just going to draw them like this. Now, one other thing I wanted to point out before we move on, though, is this position over here. Use another color. That position there, that carbon does not have any hydrogens attached to it. So we cannot get bromination there because we need a hydrogen to be abstracted by the bromine radical for the radical bromination to take place. Okay, so if we want to draw out the mechanism, we're going to get a bromine radical, single-headed arrows, fishhook arrows. We're going to form the bond like that, and we're going to generate the radical at that position there. And that is going to give us a product that looks like this. And if we want to be really complete about it, then we're going to generate HBr. So that, as I said before, is a tertiary radical, and therefore is a relatively stable compared to the primary radical that it would have been the only other possibility. So now that radical it has a number of fates, and you can look up in your textbook or online all of the different initiation, propagation, and termination events that can happen. But importantly, the main propagation event for this radical is that it will find a bromine molecule and we'll get a radical reaction like this and generate our halogenated or brominated alkane. I'll just draw that again because it's not in the same orientation as what I started with. Okay, so there's the carbon-bromine bond that we just formed, and you can see that's the product. So that reaction will give this product. So what's this question asking? If this question is just asking for the product, it's asking for you to recognize that Br2 and Hν, which is the abbreviation for light, those conditions generate bromine radicals. That leads to radical bromination, where we will replace a CH bond with a carbon-bromine bond. And furthermore, we're looking for the ability to spot that there's two types of CH bonds. There's a CH bond attached to a tertiary carbon, and then there's methyl CH bonds. And the radical will preferentially form at the tertiary position to give this tertiary alkyl bromide. Okay, so to get full marks for this kind of question in an exam, it's important to spot all those features. If, for example, you drew out a product that looked like this, that might get part marks because you've recognized that it's a radical bromination, but you've done the bromination at a less stable position, at a position that will go via a less stable metal radical. A very common mistake many students make is to not go through the whole process of looking at where are the hydrogens in this molecule and what are the possible products. And I quite often see in exam situations products that look like this. Okay, so that is not correct. This is sort of part correct, so you might get half marks. So this one up here is not correct because we've lost an entire methyl group. We've sort of the student who draws this answer have sort of exchanged out a methyl group for a bromine at this position here, and it's not, it's not doing a radical bromination at all. It's doing something that's not chemically feasible. So that kind of answer will generally get 0 in an exam situation. Okay, so hopefully you found this useful and explains a few features of this type of radical bromination question in an exam.